Hi, in this video, we'll see our project on modeling the plant of the F110 simulator using the synchronous reactive component. Uh, so before starting, let's first see what a synchronous reactive component in a very basic term is. So for a synchronous reactive component, we have a set of inputs, and then the component might have a set of state variables. These state variables will be updating based on the inputs, and then the component has to compute an output and release the output. That is the very basic definition, or the very basic view of the synchronous reactive component. So in our case, we have to define the synchronous reactive component for the plant of the F110 simulator. So this is the F110 simulator, and we have to define the plant for this simulator. Yeah. So the plant is basically constituted of four synchronous reactive components: the simulator, the multiplexer, the behavior controller, and the joysticks, or basically the planners. These all are the planners. So let's look at what the input and the state variables and the output of each of the synchronous reactive components are. So the simulator basically takes in input from the multiplexer, and the input is basically the drive messages in terms of what the speed should be, or what should be the steering angle, all these things, and it has to compute the next state of the car, the position of the car, or the velocity, or the if there is that's all. And the output is basically a laser scan, a lidar scan, which it does. The updation is basically in the paper. The updation is done basically via via the bicycle model dynamics. The second synchronous reactive component model is the multiplexer. The multiplexer basically takes an input from two things: from the planners, the joystick, keyboard, and all the below things are the planners, and the behavior controller. These two things are there. So the planners basically give the drive messages as the input, and the behavior controller gives the selector input. So for a multiplexer to work, the selector input basically tells the multiplexer which of the input it should allow to pass through. So whatever the simulator is getting as the input is basically one of the inputs the multiplexer is getting. And these inputs basically are controlled by the behavior controller. There are all like not very significant state variables in here. So as they do not modify or change, or the change inputs, or maybe affect the output. These basically the state variables in this case are basically the indexes, like where the keyboard, the index for the keyboard, the index for the random driver, and all. The output is, as I said, is one of the inputs basically. So it is a kind of uh, uh, it is a kind of combinational reactive component. Yes, it is a kind of combinational reactive component. The next reactive component is behavior controller. So behavior controller outputs, as I said, the selector value for the mux, which depends on the two things: the inputs coming from the planners, which are basically the on and off signals, and the sensors. So the behavior controller can be configured to use the sensors value as well, but in a basic setting, it is basically used for the on and off state of the from the other motion planners. The state variables here is also negligible, like they do not affect the output of the component here. Yes. So finally, the planners are basically the important part. These are the most configurable part in the whole plant model. The planners is the only reactive component system which whose state is like the core of the whole simulation. So the input is basically the lidar point cloud. So the simulation, as I told before, the simulation outputs a laser scan of the environment, and then the values when they come back as a point cloud, those are the inputs to the motion planners. So there can be different types of motion planners. Basically, if for the simulation, we have two types. The first one is the manual motion planner, like the joystick and the keyboard are the manual motion planners, and the second one is the automated motion planner, which are basically the code. So you could have a neural network which drives the whole vehicle, or you could have certain algorithms, the routing algorithms, which drives the vehicle based on the sensor readings. So those are the automated motion planners. The other motion planners are the keyboard or the joystick. So it depends. The neural network part of the F110 basically comes here in the planner. The input is, as I told, the lidar point cloud, and the state is basically based on the racing strategy, and the output is one of the based on one of these strategies. The output would be some kind of a velocity value or some kind of an acceleration value, not the actual point position of the vehicle, which is done by the simulator, but the velocity. Okay, so yeah, so we can have two examples, like there could be a random planner which moves like the based on the sensor reading, which moves the vehicle, which sets the value of velocity randomly. Or we could have an auto e-brake which basically takes the sensor reading and moves the vehicle until there is not a wall or a roadblock, and if there is a roadblock or wall surrounding the vehicle, it just stops the vehicle. It outputs a brake message, which is also transmitted to the behavior controller, which is also transmitted to behavior control, so that it just switches off the mux, and thus the vehicle stops, as nothing is going to reach to the simulator. Yes. So we'll see this. Yeah. So for each of the reactive components, there are different files. The CPP files are the codes for the reactive components. Uh, we have basic behavior controller. All the state variables and the inputs and outputs of the functions are being defined in these files. The keyboard.cpp and randomwalk.cpp are basically the planner component. The mux is the multiplexer component, and the simulation is the simulator component. Yes. So all the state variables and all the inputs and outputs basically are defined in this file. Now let's jump to the simulation. So this is what the simulation of the F110 looks like. So basically we have a vehicle here, we have a map, we can change the map. There are multiple options to do that. We can do all the sort of settings possible. So but let's see, if we are using a keyboard as the motion planner, so how do we do that? So if I am using keyboard as a motion planner, I first use the K key on the keyboard, which basically turns on the keyboard. You can see the mux output in the two cases when none of the inputs were given, like there were no planners at all, so all were zero. Now there is the keyboard planner switched on. So this planner is being this value of that this planner is switched on is being given to the behavior controller, which takes in the value that which of the planner is switched on basically. So yes, um, yeah. So the when the keyboard planner is switched on, I can give the keyboard planner input as WASD. If I give the input as S, then it moves backward, which basically then goes through the multiplexer, and then finally the simulator, which calculates the velocity and the position of the vehicle. And I can change the value to A so that it moves on the left, like now. And you can see the coloring of the wall is being done because of the lidar sensor. In the case when we are using the keyboard planner, we are not as such using the the sensor readings because we are controlling it manually. But if we were to write an automated code based on the neural network part, which is not in the scope of this course, then these readings will come into picture. So yes, so we have, so yeah, also certain time when there is a collision happening, the multiplexer just switches off, because that is also based on the reactive behavior controller. The behavior controller takes the readings as input, and it sees that there is a collision happened, so it just switches off the multiplexer. So yeah, that's it for the whole project. So to just summarize, we have four components, four synchronous reactive components. Each component, I kind of described the inputs, the state variables, and the outputs for each of the components and the working. and saw the simulation, and also we saw the actual code part of it. There is also some code part of it, like we have this kinematics.cpp which does the cosine and computes uh, all the uh, velocity values and the position values based on the equations given in the dynamics model and the observation model. So yes, that's all from our side. So the team has me, Siddhant, and Ishan. Yeah, that's it. Thank you.